In the autumn of 1926, the world's greatest minds gathered in Brussels for what would become one of the most consequential conferences in the history of science. The Fifth Solvay Conference brought together physicists who were grappling with discoveries that challenged everything humanity thought it knew about reality. Among them sat a young Werner Heisenberg, whose uncertainty principle would soon shake the foundations of classical physics, and Niels Bohr, the Danish physicist whose interpretation of quantum mechanics would dominate scientific thinking for decades. But it was Albert Einstein, already a legend at 47, who would voice the most profound objection to the strange new physics emerging from their laboratories. The man who had revolutionized our understanding of space and time with relativity was deeply uncomfortable with what quantum mechanics seemed to suggest about the nature of reality itself. While his colleagues embraced a universe governed by probability and uncertainty, Einstein clung to his belief that God does not play dice with the cosmos. The source of Einstein's discomfort lay in the heart of quantum mechanics, a theory that had proven remarkably successful at predicting the behavior of atoms and subatomic particles. According to this new framework, particles existed in a ghostly state called superposition, where they could simultaneously possess multiple properties until the moment someone measured them. A particle could spin both clockwise and counterclockwise at the same time, existing in all possible states until observation forced it to choose one. This concept defied common sense and challenged our most basic intuitions about reality. In our everyday world, a coin is either heads or tails, never both. A cat is either alive or dead, not suspended in some twilight state between life and death. Yet quantum mechanics insisted that at the microscopic level, such impossible-seeming situations were not only possible, but inevitable. The Copenhagen interpretation, championed by Bohr and his colleagues, offered an explanation that was as elegant as it was unsettling. They argued that quantum systems don't have definite properties until they're measured. The act of observation itself causes the wave function, the mathematical description of all possible states, to collapse into a single outcome. Before measurement, particles exist in a fuzzy cloud of probability. After measurement, they crystallize into definite reality. Einstein found this interpretation philosophically repugnant. He believed in an objective reality that existed independent of human observation. Somewhere beneath the apparent randomness of quantum mechanics, he was convinced lay hidden variables that determined the outcomes of experiments. If scientists could only uncover these hidden mechanisms, they would restore determinism to physics and banish the troubling specter of fundamental uncertainty. The debate reached its crescendo in 1935 when Einstein, working with two younger colleagues, Boris Podolsky and Nathan Rosen, published a paper that would forever change how physicists thought about quantum mechanics. Their paper, titled "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?", presented what became known as the EPR paradox, named after the initials of its three authors. The EPR argument was deceptively simple yet devastatingly effective. Einstein and his collaborators imagined a scenario where two particles interact briefly and then fly apart to opposite ends of the universe. According to quantum mechanics, these particles would remain connected in a mysterious way called entanglement. Measuring one particle would instantly determine the properties of its partner, no matter how far apart they had traveled. Consider two particles that were once paired, now separated by millions of kilometers. Quantum mechanics predicted that if you measured the spin of one particle and found it spinning clockwise, you would instantly know that its partner must be spinning counterclockwise. The measurement of one particle would somehow instantaneously affect its distant companion, transmitting information faster than the speed of light. This prospect horrified Einstein. His theory of special relativity had established that nothing could travel faster than light, not matter, not energy, not even information. The speed of light wasn't just a cosmic speed limit, it was woven into the very fabric of space and time. To violate this limit would mean tearing apart the elegant structure of relativity that Einstein had spent decades constructing. Einstein dismissed this supposed instantaneous connection between distant particles as spukhafte Fernwirkung, a German phrase that translates to spooky action at a distance. The term perfectly captured his skepticism and disgust at what he saw as an absurd consequence of an incomplete theory. Surely, Einstein reasoned, the particles must carry hidden information from the moment they separate, like secret instructions that predetermine their behavior when measured. To illustrate his point, Einstein often used the analogy of a pair of gloves. Imagine you have two gloves, one left-handed and one right-handed, placed in separate boxes and shipped to opposite sides of the world. When someone opens one box and finds a left-handed glove, they instantly know the other box contains a right-handed glove. But this isn't magic or mysterious action at a distance. The gloves possess their properties from the moment they were separated. Einstein believed quantum entanglement worked the same way. The particles weren't mysteriously communicating across vast distances. They simply carried hidden variables, like invisible labels, that predetermined their behavior. When scientists developed more sophisticated instruments, Einstein predicted, they would uncover these hidden variables and restore sensible, local causality to physics. Bohr and his supporters vigorously defended quantum mechanics against Einstein's attack. They argued that the EPR thought experiment, while clever, missed the fundamental point about quantum reality. Unlike classical gloves, quantum particles genuinely don't possess definite properties until measured. The act of measurement on one particle doesn't reveal pre-existing information. It creates the very property being measured and simultaneously determines the fate of its entangled partner. The debate between Einstein and Bohr raged for years, fought through scientific papers, conference presentations, and private correspondence. Both sides marshaled sophisticated arguments, but neither could definitively prove their position. The EPR paradox remained a philosophical puzzle rather than an experimentally testable question. What made the controversy so intractable was that both interpretations made identical predictions about experimental outcomes. Whether you believed in hidden variables or genuine quantum weirdness, you would expect to see the same results in the laboratory. The dispute seemed destined to remain forever in the realm of philosophy, rather than empirical science. Yet, even as the debate raged, a few prescient physicists realized that quantum entanglement, if real, could have profound implications for human technology and our understanding of the universe. In 1935, the same year as the EPR paper, Erwin Schrödinger introduced the term entanglement and explored its implications in a series of papers that laid the groundwork for what would eventually become quantum information theory. Schrödinger, the Austrian physicist famous for his equation describing quantum wave functions, was initially as skeptical as Einstein about the implications of entanglement. He devised his famous thought experiment involving a cat in a box to illustrate what he saw as the absurdity of applying quantum superposition to macroscopic objects. But as he delved deeper into the mathematics, Schrödinger began to appreciate the profound nature of quantum entanglement. When two systems, of which we know the states by their respective representatives, enter into temporary physical interaction due to known forces between them, and when after a time of mutual influence the systems separate again, Schrödinger wrote, then they can no longer be described in the same way as before visi, by endowing each of them with a representative of its own. I would not call that one, but rather the characteristic trait of quantum mechanics, the one that enforces its entire departure from classical lines of thought. Schrödinger's insight was remarkable. He recognized that entanglement wasn't just a curious side effect of quantum mechanics. It was the feature that most clearly distinguished quantum physics from classical physics. In the classical world, objects maintain their independence even after interacting. A billiard ball that strikes another ball and bounces away retains its own distinct identity and properties. But in the quantum world, particles that interact can become fundamentally connected, losing their individual identities and forming a single, indivisible quantum system. As the 1930s drew to a close, the scientific community remained divided. Einstein continued his search for hidden variable theories that could restore determinism and locality to physics. Meanwhile, younger physicists like John von Neumann and others began exploring the mathematical foundations of quantum mechanics, proving theorems that seemed to rule out certain types of hidden variable theories. But the ultimate resolution of the EPR debate would have to wait for a new generation of physicists who would develop the tools and insights necessary to test Einstein's ideas experimentally. The stage was set for a confrontation between theory and experiment that would take decades to resolve and would ultimately reveal truths about the universe stranger than either Einstein or Bohr had imagined. The seeds of that future revolution were already present in the work of the 1930s pioneers. They had identified the key questions about the nature of quantum reality and had begun to develop the mathematical frameworks that would eventually allow those questions to be answered definitively. What they couldn't have foreseen was that the resolution would come not through pure thought or mathematical proof, but through ingenious experiments that would push the boundaries of technology and reveal the quantum world in all its bizarre glory. As we look back on this pivotal moment in the history of physics, we can see that both Einstein and Bohr were partially correct. Einstein was right to insist that any complete theory of physics must be consistent with relativity and must provide a clear account of physical reality. But Bohr was right to recognize that quantum mechanics revealed something genuinely new about the nature of that reality, something that couldn't be reduced to classical concepts no matter how cleverly they were applied. The story of quantum entanglement is ultimately a story about the evolution of human understanding, about the gradual recognition that the universe operates according to principles that transcend our everyday experience and challenge our most basic intuitions about the nature of existence itself. For nearly 3 decades after Einstein's challenge to quantum mechanics, the EPR paradox remained locked in philosophical limbo. The greatest minds in physics had argued passionately about the nature of reality, but their debates seemed destined to continue forever, without resolution. Then, in 1964, a quiet physicist working at CERN, the European Particle Physics Laboratory near Geneva, published a paper that would transform the philosophical debate into an experimental battleground. John Stuart Bell was not a household name in physics. Born in Belfast in 1928, he had grown up in a working-class family and earned his degree from Queen's University Belfast before moving to England for graduate work. Unlike Einstein or Bohr, Bell was not a charismatic figure who commanded international attention. He was a thoughtful, methodical physicist who preferred to work behind the scenes, tackling problems that others had dismissed as unsolvable. Bell had been fascinated by the foundations of quantum mechanics since his student days. While most physicists had moved on to other problems, accepting the Copenhagen interpretation as the final word on quantum reality, Bell remained troubled by the same questions that had bothered Einstein. Was quantum mechanics really complete, or did hidden variables lurk beneath the surface of physical phenomena? The breakthrough came when Bell realized that the EPR debate, for all its sophistication, had missed a crucial point. Einstein and his supporters had argued that local hidden variables could explain quantum correlations without requiring spooky action at a distance. But they had never specified exactly what predictions such theories should make. Bell set out to determine precisely what experimental results would be expected if local hidden variable theories were correct. Bell's insight was to focus on a specific type of quantum entanglement experiment involving measurements along different axes. Imagine 2 entangled particles flying apart in opposite directions. Each particle carries a quantum property called spin, which can be measured along any axis you choose. In a typical experiment, you might measure one particle's spin along a vertical axis while measuring its partner's spin along a diagonal axis. According to quantum mechanics, the results of these measurements should be correlated in a specific way that depends on the angles between the measurement axes. The theory makes precise mathematical predictions about how often the two particles should give matching results when measured along different combinations of axes. Bell realized that any theory based on local hidden variables would have to satisfy certain mathematical constraints. These constraints arose from the simple requirement that information cannot travel faster than light. If the particles carried hidden variables that predetermined their measurement outcomes, and if these variables were established when the particles first separated, then the correlations between distant measurements should obey what became known as Bell's inequality. The mathematics behind Bell's inequality is elegant in its simplicity, though its implications are profound. Consider three different measurement axes, which we can call A, B, and C. Bell showed that if local hidden variables determine measurement outcomes, then the correlations between measurements must satisfy a specific mathematical relationship. The sum of correlations between axes A and B, plus the correlation between axes B and C, must be greater than or equal to the correlation between axes A and C minus 1. This inequality represented a fundamental limitation on what any local hidden variable theory could predict. It was like drawing a line in the sand, separating the realm of classical, local physics from something more exotic. Theories that respected the speed of light limit and assumed predetermined particle properties had to stay on one side of this line. Quantum mechanics, with its predictions of instantaneous correlations, fell on the other side. Bell's theorem established that quantum mechanics and local hidden variable theories make different predictions about the outcomes of certain experiments. This was revolutionary because it meant the 30-year-old philosophical debate could finally be settled in the laboratory. Nature herself would serve as the ultimate judge, revealing through experimental results whether Einstein's vision of local realism or the quantum mechanical picture of reality was correct. The key insight was that quantum mechanics predicts correlations that violate Bell's inequality. According to the quantum theory, when you measure entangled particles along carefully chosen axes, you should observe correlations that are stronger than any local hidden variable theory could explain. The violation wouldn't be subtle or marginal, it would be clear and unambiguous, providing a decisive test of competing theories. To understand why this violation occurs, consider what happens when quantum mechanics makes its predictions. Unlike hidden variable theories, quantum mechanics doesn't assume that particles carry predetermined answers to all possible measurement questions. Instead, the theory treats measurement as a fundamentally creative act that brings properties into existence. When you measure one entangled particle, you don't just reveal a pre-existing property, you collapse the shared wave function of both particles, instantly determining the measurement outcome for its distant partner. This process of wave function collapse allows quantum mechanics to achieve correlations that seem impossible from a classical perspective. The particles aren't carrying hidden messages that coordinate their responses. Instead, they remain connected through their shared quantum state, which contains more information than could be stored in any collection of local hidden variables. Bell's work revealed that this quantum mechanical picture makes predictions that are not just different from classical physics, but demonstrably different. The violation of Bell's inequality would serve as a signature of genuine quantum non-locality, proof that nature operates according to principles that transcend our classical intuitions about space, time, and causality. But Bell's theorem was more than just a clever mathematical trick. It illuminated fundamental features of quantum mechanics that had been hidden since the theory's inception. Bell showed that quantum entanglement wasn't just weird or counterintuitive, It was genuinely non-local in a way that could be precisely defined and experimentally tested. The correlations between entangled particles couldn't be explained by any theory that respected both realism, the idea that particles have definite properties, independent of measurement and locality, the requirement that influences cannot propagate faster than light. This insight forced physicists to confront a stark choice. Either quantum mechanics was wrong, or one of humanity's most cherished assumptions about the nature of reality had to be abandoned. Either particles don't have definite properties until measured, violating realism, or measuring one particle can instantly affect its distant partner, violating locality. There was no middle ground, no clever compromise that could preserve both classical realism and relativistic locality. Bell himself was initially skeptical that his inequality would be violated in real experiments. Like Einstein, he favored local hidden variable theories and hoped that experiments would eventually reveal the classical mechanisms underlying quantum phenomena. But he had provided the tools necessary to settle the question definitively, regardless of his personal preferences. The experimental challenges were formidable. Testing Bell's inequality required creating pairs of entangled particles, separating them by significant distances, and performing precise measurements along different axes with perfect timing and coordination. The technology of the 1960s was barely adequate for such demanding experiments, but a new generation of physicists was eager to take up Bell's challenge. The first attempts to test Bell's inequality came in the early 1970s. Stuart Friedman and John Clauser, working at the University of California, Berkeley, designed an experiment using entangled photons created by atomic transitions. Their setup was ingenious, but technically demanding, requiring careful calibration of optical components and sophisticated electronics to register the fleeting signals from individual photons. The Friedman-Clauser experiment provided the first clear evidence that Bell's inequality could indeed be violated in nature. Their results strongly supported quantum mechanics and cast doubt on local hidden variable theories. But the experiment also revealed the enormous technical challenges involved in testing Bell's theorem with sufficient precision and rigor to convince skeptics. The early experiments, while groundbreaking, suffered from various loopholes that allowed determined advocates of hidden variable theories to maintain their position. The detection efficiency loophole arose because photon detectors of that era missed many of the particles they were supposed to register. Critics argued that hidden variable theories could be constructed to exploit this inefficiency, producing results that appeared to violate Bell's inequality while actually respecting it. The locality loophole was even more serious. In early experiments, the measurement settings on both detectors were determined before the entangled particles were created. This meant that hidden variable theories could potentially exploit advanced knowledge of the measurement configuration to produce correlations that mimicked quantum mechanical predictions without requiring any non-local influences. Despite these loopholes, the accumulating experimental evidence strongly favored quantum mechanics over local hidden variable theories. Each new experiment refined the techniques and closed additional loopholes, making it increasingly difficult to maintain belief in classical alternatives to quantum mechanics. But the ultimate vindication of Bell's insights would require decades of technological development and experimental refinement. Bell's theorem had transformed the landscape of fundamental physics. What had begun as a philosophical debate about the interpretation of quantum mechanics had become an active area of experimental research, with profound implications for our understanding of reality. The theorem established quantum non-locality as a testable scientific hypothesis, rather than merely a philosophical speculation. More broadly, Bell's work demonstrated the power of careful mathematical analysis to illuminate conceptual problems that had seemed purely philosophical. By translating vague notions about hidden variables and local realism into precise mathematical statements, Bell had opened up new avenues for experimental investigation and theoretical development. The implications extended far beyond the narrow question of whether quantum mechanics was correct. Bell's theorem revealed that any complete description of physical reality must incorporate some form of non-locality or abandon the assumption that particles possess definite properties independent of measurement. This insight would prove crucial for the development of quantum information theory and quantum technologies that would emerge in subsequent decades. As word of Bell's theorem spread through the physics community, it sparked renewed interest in the foundations of quantum mechanics. Young physicists who had been taught to accept the Copenhagen interpretation without question began to reconsider the conceptual basis of their field. The theorem provided a concrete framework for investigating questions about the nature of reality that had been relegated to philosophy textbooks. Bell himself remained characteristically modest about his achievement. He continued to work on other problems in particle physics and maintained his skepticism about some interpretations of quantum mechanics. But he had provided the scientific community with an invaluable gift: a clear, testable criterion for distinguishing between classical and quantum descriptions of nature. The laboratory in Orsay, just south of Paris, buzzed with quiet intensity in the early 1980s. Inside a carefully shielded room, Alain Aspect and his team were preparing to conduct what many considered the most important physics experiment of the century. Their goal was audacious: to test Bell's inequality with such precision and rigor that no reasonable doubt could remain about the nature of quantum reality. Aspect, a young French physicist with an infectious enthusiasm for fundamental questions, had become obsessed with Bell's theorem during his graduate studies. While most experimentalists focused on discovering new particles or phenomena, Aspect was drawn to the deeper question of whether the universe operated according to classical principles or the bizarre rules of quantum mechanics. He understood that settling this question would require experimental precision and ingenuity far beyond what had been achieved before. The technical challenges were staggering. Testing Bell's inequality demanded creating pairs of perfectly entangled photons, sending them in opposite directions to separate detection stations, and measuring their properties with exquisite timing and precision. Every component of the apparatus had to work flawlessly, because any systematic error or inefficiency could undermine the entire experiment and leave room for classical explanations of the results. Aspect's breakthrough insight was to use a special type of atomic transition that naturally produces pairs of entangled photons. When calcium atoms are excited by laser light, they sometimes emit two photons simultaneously in a process called cascade emission. These twin photons fly apart in opposite directions, carrying entangled polarization states that remain mysteriously connected no matter how far they travel. The genius of Aspect's design lay in his solution to the locality loophole that had plagued earlier experiments. Previous tests of Bell's inequality had used fixed measurement settings that were determined before the entangled particles were created. Critics argued that this allowed enough time for classical signals to coordinate the measurement outcomes, making it impossible to rule out local hidden variable theories definitively. Aspect solved this problem by switching the measurement settings randomly and rapidly while the photons were in flight between their source and the detectors. Using high-speed optical switches that could change the measurement axis in just 10 nanoseconds, he ensured that the measurement choice for each photon was made after the particles had already been created and begun their journey. This eliminated any possibility that classical signals traveling at the speed of light could coordinate the measurement outcomes. The experimental setup resembled something from a science fiction movie. Twin laser beams crossed in a sealed chamber containing calcium vapor, creating the conditions for entangled photon emission. The resulting photon pairs raced through carefully aligned optical systems toward detection stations located several meters apart. Along the way, rapidly switching polarization analyzers randomly selected the measurement axis for each photon, ensuring that the choice couldn't be predetermined by hidden classical mechanisms. At each detection station, sensitive photomultiplier tubes registered the arrival of individual photons, recording their polarization with nanosecond precision. Sophisticated electronics correlated the detection events, building up statistics about how often the measurements on paired photons agreed or disagreed when analyzed along different axes. The moment of truth came when Aspect's team analyzed their accumulated data. After thousands of photon pair measurements, the pattern was unmistakable. Bell's inequality was violated by exactly the amount predicted by quantum mechanics. The correlations between entangled photons were stronger than any local hidden variable theory could explain, providing clear evidence that nature operates according to genuinely non-local principles. The violation wasn't subtle or marginal. Quantum mechanics predicted a maximum correlation strength of about 1.414, represented by the square root of 2, while local hidden variable theories were limited to correlations no stronger than 1.0. Aspect's measurements consistently showed correlations near the quantum mechanical limit, decisively ruling out classical alternatives. News of Aspect's results electrified the physics community. Here was experimental proof that Einstein had been wrong about the completeness of quantum mechanics and the possibility of local hidden variable theories. The universe really did exhibit spooky action at a distance, with measurements on one particle instantly affecting the properties of its distant partner. But Aspect's work was just the beginning. Over the following decades, a new generation of experimentalists would push the boundaries of Bell inequality tests to ever greater extremes, closing loopholes and extending the reach of quantum non-locality demonstrations across increasingly vast distances. One of the most significant challenges was the detection efficiency loophole. Early photon detectors missed most of the particles they were supposed to register, detecting only a small fraction of the photons produced by entangled sources. Critics argued that hidden variable theories could exploit this inefficiency, producing results that appeared to violate Bell's inequality, while actually respecting it in the undetected events. Closing this loophole required developing new types of detectors with near-perfect efficiency and conducting experiments with different types of entangled particles. Teams around the world began working with entangled atoms, ions, and other quantum systems that could be detected more reliably than photons. These experiments consistently confirmed the violation of Bell's inequality, providing additional evidence that quantum non-locality was a genuine feature of nature rather than an artifact of experimental limitations. The locality loophole also required continued attention as experimental distances grew longer, while Aspect's switching experiment had eliminated the possibility of light-speed coordination over laboratory distances. Critics pointed out that truly convincing tests required separating the measurement stations by much larger distances, making any classical coordination impossible even in principle. Anton Zeilinger, an Austrian physicist who had worked with Aspect in the early days, took up this challenge with characteristic boldness. Zeilinger's team conducted Bell inequality tests across the Danube River in Vienna, separating their detectors by hundreds of meters and later by several kilometers. Each extension in distance made classical explanations increasingly implausible and strengthened the case for genuine quantum non-locality. The experimental techniques continued to evolve throughout the 1990s and 2000s. Researchers developed new methods for creating entangled particles, improved detection systems, and refined the statistical analysis techniques used to extract Bell inequality violations from experimental data. Each refinement brought new precision to the measurements and closed additional loopholes that skeptics might exploit. One of the most dramatic developments came with the advent of space-based quantum experiments. Teams in China and Europe began launching satellites equipped with quantum sources and detectors, enabling Bell inequality tests across distances of hundreds and eventually thousands of kilometers. These experiments not only demonstrated quantum non-locality over unprecedented distances, but also laid the groundwork for practical quantum communication networks. The Messier satellite, launched by China in 2016, marked a milestone in space-based quantum experiments. Named after an ancient Chinese philosopher, the satellite could create entangled photon pairs and beam them down to ground stations separated by more than 1,000 kilometers. The resulting Bell inequality violations were measured with extraordinary precision, ruling out local hidden variable theories with confidence levels that exceeded 10 standard deviations. Perhaps the most definitive closure of experimental loopholes came in 2015, when 3 independent research groups simultaneously published what became known as loophole-free Bell inequality tests. These experiments, conducted in Vienna, Boulder, and Delft, used different experimental approaches, but reached the same conclusion. Quantum mechanics accurately describes the correlations between entangled particles, and local hidden variable theories are definitively ruled out. The Vienna experiment, led by Zeilinger's group, used entangled photons detected at stations separated by 1.3 kilometers. High-efficiency detectors and rapid random switching of measurement settings eliminated both the detection and locality loopholes simultaneously. The measured Bell inequality violation was statistically significant beyond any reasonable doubt. Meanwhile, the Boulder experiment, conducted by researchers at the National Institute of Standards and Technology, used entangled ions trapped in separate laboratories. The exceptional detection efficiency possible with trapped ions allowed them to close the detection loophole completely while maintaining spatial separation sufficient to eliminate locality concerns. The Delft experiment took yet another approach, using entangled electron spins in diamond crystals separated by 1.3 kilometers. This solid-state approach demonstrated that Bell inequality violations weren't limited to photons or atoms, but represented a universal feature of quantum entanglement, regardless of the specific physical system involved. The accumulation of evidence from these and dozens of other experiments created an overwhelming scientific consensus. Bell's inequality is indeed violated in nature. Quantum mechanics correctly describes the correlations between entangled particles, and local hidden variable theories are incompatible with experimental observations. The debate that had raged for decades was finally settled in favor of quantum non-locality. Recognition of this achievement came in 2022, when the Nobel Prize in Physics was awarded to Alain Aspect, John Clauser, and Anton Zeilinger for their pioneering experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. The Nobel Committee explicitly recognized their role in transforming quantum entanglement from a philosophical puzzle into a cornerstone of modern physics and technology. The experimental proof of Bell inequality violations had profound implications that extended far beyond the narrow question of whether quantum mechanics was correct. It established non-locality as a fundamental feature of physical reality, forcing physicists to abandon either the assumption that particles have definite properties independent of measurement or the requirement that influences cannot propagate faster than light. Most physicists chose to abandon local realism while preserving the speed of light limit by accepting that quantum measurements don't reveal pre-existing properties, but rather create the very properties they measure. This interpretation preserves relativistic causality because no useful information can be transmitted faster than light using quantum entanglement, even though the correlations themselves appear to be instantaneous. The experiments also revealed the extraordinary fragility of quantum entanglement. The entangled states that violate Bell's inequality are easily destroyed by environmental interference, a process called decoherence. Maintaining entanglement over large distances and long times requires extraordinary isolation from external disturbances, highlighting both the fundamental importance of entanglement and the technical challenges involved in exploiting it. Yet these same experiments that proved the impossibility of local hidden variable theories also demonstrated the possibility of new technologies based on quantum non-locality. The precise control over entangled particles required for Bell inequality tests laid the groundwork for quantum communication, quantum cryptography, and quantum computing. What began as a test of fundamental physics principles evolved into the foundation for a technological revolution. As the experimental evidence mounted and the scientific consensus solidified, physicists began to grapple with the deeper implications of quantum non-locality. If the universe really operated according to the principles revealed by Bell inequality violations, what did this mean for our understanding of space, time, and causality? How could particles separated by vast distances maintain perfect correlations without exchanging information? And what did quantum entanglement reveal about the fundamental structure of reality itself? With the experimental proof of Bell inequality violations firmly established, physicists faced a new challenge: understanding exactly how quantum entanglement works and why it produces such startling correlations between distant particles. The experiments had definitively shown that nature violates local realism, but they hadn't explained the underlying mechanism that makes such violations possible. To truly comprehend entanglement, we need to dive deep into the quantum mechanical description of reality and explore how it differs so radically from our classical intuitions. The story begins with the concept of quantum superposition, perhaps the most counterintuitive aspect of quantum mechanics. In our everyday world, objects have definite properties at all times. A spinning coin is either heads or tails, a traffic light is either red or green, and a door is either open or closed. But in the quantum world, particles can exist in superposition states, where they simultaneously possess multiple contradictory properties until the moment someone measures them. Consider a single photon approaching a polarizing filter. In classical physics, we would expect the photon to have a definite polarization direction, either aligned with the filter or perpendicular to it. If aligned, the photon passes through. If perpendicular, it gets blocked. But quantum mechanics tells a different story. Before measurement, the photon exists in a superposition of all possible polarization states, neither definitively aligned nor perpendicular to the filter, but somehow both and neither simultaneously. This superposition isn't just a limitation of our knowledge or measurement capabilities. According to quantum mechanics, the photon genuinely doesn't have a definite polarization until the measurement forces it to choose. The act of measurement causes what physicists call wave function collapse, where the fuzzy cloud of possibilities crystallizes into a single definite outcome. Mathematically, quantum superposition is represented by the wave function, a complex mathematical object that encodes all possible measurement outcomes and their associated probabilities. For a single particle, the wave function might look deceptively simple, but it contains a wealth of information about the quantum state and predicts the statistical outcomes of any measurement you might perform. When two particles become entangled, their individual wave functions merge into a single, shared quantum state that cannot be separated into independent parts. This is where entanglement reveals its truly mysterious nature. The entangled particles lose their individual identities and become components of a unified quantum system, even when separated by vast distances. To understand how this works, imagine two photons created simultaneously in a process that conserves certain physical quantities, like total angular momentum. Conservation laws are fundamental principles of physics that require certain properties to remain constant in isolated systems. When two photons are born from a single quantum event, their combined properties must satisfy these conservation requirements. If the total angular momentum of the original system was zero, then the two photons must carry equal and opposite angular momentum. But here's where quantum mechanics becomes truly strange. Neither photon has a definite angular momentum until measured. Instead, they exist in an entangled superposition where all possible combinations of angular momentum that satisfy the conservation law are simultaneously present. The entangled state might be described as a quantum superposition, where photon A has clockwise spin while photon B has counterclockwise spin, combined with another possibility where photon A has counterclockwise spin while photon B has clockwise spin. These two possibilities coexist in the quantum superposition, with neither being more real than the other until a measurement collapses the wave function. When you measure the spin of photon A and find it rotating clockwise, the wave function instantly collapses throughout the entire entangled system. Photon B immediately acquires the opposite spin direction, ensuring that the conservation law is satisfied. This collapse happens instantaneously, regardless of the distance separating the particles, leading to the mysterious correlations that violate Bell's inequality. The key insight is that entanglement doesn't involve sending signals or information between the particles. Instead, it represents a form of shared existence where the particles remain part of a single quantum system despite their spatial separation. The measurement doesn't reveal pre-existing properties or trigger communication between distant particles. Rather, it creates the very properties being measured throughout the entire entangled system. This process preserves the fundamental principles of special relativity, even though it appears to involve instantaneous action at a distance. The resolution lies in recognizing that no useful information can be transmitted using quantum entanglement alone. When you measure photon A and collapse the entangled wave function, you get a random outcome that you cannot control or predict in advance. Your measurement instantly determines the outcome that will be observed at photon B, but since your result is random, you cannot use this process to send messages faster than light. To send information using entanglement, you would need to communicate through classical channels that respect the speed of light limit. You might call your colleague and tell them what result you observed, allowing them to interpret their own measurement outcomes. But the quantum correlations by themselves cannot carry any meaningful message from one location to another. The mathematics of entanglement reveals why the correlations are so much stronger than classical physics allows. In local hidden variable theories, correlations are limited by the assumption that each particle carries predetermined answers to all possible measurement questions. The strength of correlations in such theories is constrained by the fact that particles can only give consistent answers that don't depend on measurements performed elsewhere. Quantum entanglement escapes these limitations because the particles don't carry predetermined answers. Instead, the act of measurement creates correlated outcomes throughout the entangled system. This allows quantum mechanics to achieve correlations that approach the mathematical maximum possible for any physical theory, reaching values near the square root of 2 that decisively violate Bell's inequality. The process of decoherence plays a crucial role in understanding why entanglement is so fragile and why we don't observe quantum superposition in everyday life. When quantum systems interact with their environment, they rapidly lose their coherent superposition states and behave more like classical objects with definite properties. This environmental interaction acts like a continuous measurement process that collapses quantum superpositions and destroys entanglement. For entangled particles to maintain their mysterious correlations, they must be carefully isolated from environmental disturbances. Even minute interactions with stray photons, magnetic fields, or vibrations can disrupt the delicate quantum state and reduce the observed correlations toward classical values. This is why quantum entanglement experiments require such extraordinary control over experimental conditions, and why scaling up quantum technologies to practical applications remains challenging. The timescale for decoherence depends on the specific quantum system and its environment. Photons traveling through empty space can maintain entanglement over vast distances because they interact very weakly with their surroundings. But particles trapped in solid materials or dense gases typically lose their quantum coherence much more rapidly, sometimes in microseconds or even nanoseconds. Understanding decoherence has led to important insights about the boundary between quantum and classical physics. Large objects contain enormous numbers of particles that interact constantly with their environment and with each other. These interactions cause rapid decoherence that suppresses quantum superposition states and makes large objects behave according to classical physics. This explains why we never see macroscopic objects in quantum superposition, even though the fundamental laws of physics are quantum mechanical. The phenomenon of entanglement also illuminates the role of measurement in quantum mechanics. Unlike classical physics, where measurement simply reveals pre-existing properties, quantum measurement is a creative process that brings properties into existence. The measuring apparatus becomes entangled with the quantum system being measured, causing the combined system to evolve in ways that produce definite outcomes. This measurement process is itself governed by quantum mechanics, though the details are complex and still not fully understood in all circumstances. What is clear is that measurement involves an irreversible interaction between the quantum system and a classical measuring device, resulting in the amplification of quantum scale effects to macroscopic scales where they can be recorded and interpreted. The many worlds interpretation of quantum mechanics offers a radically different perspective on entanglement and measurement. According to this interpretation, wave function collapse never actually occurs. Instead, all possible measurement outcomes happen simultaneously in parallel universes that branch off from each other whenever a quantum measurement takes place. Entanglement correlations arise because the branching process affects all parts of an entangled system simultaneously, ensuring that correlated outcomes occur in each branch. While the many worlds interpretation remains controversial and unproven, it illustrates how different conceptual frameworks can account for the same experimental observations. Regardless of which interpretation you prefer, the mathematical formalism of quantum mechanics makes precise predictions about entanglement correlations that have been verified to extraordinary precision in countless experiments. The study of entanglement has also revealed deep connections between quantum mechanics and information theory. Entangled states can be viewed as a form of quantum information that is distributed across multiple particles, but cannot be localized to any individual component. This perspective has led to new ways of thinking about quantum states and has inspired the development of quantum information technologies. Quantum entanglement represents a fundamental resource that can be consumed and manipulated to perform tasks that are impossible with classical systems. Protocols for quantum teleportation, quantum cryptography, and quantum computing all rely on the unique properties of entangled states to achieve capabilities that transcend classical limitations. As our understanding of entanglement has deepened, it has become clear that this phenomenon represents more than just a curious feature of quantum mechanics. Entanglement appears to be a fundamental aspect of how information is processed and transmitted in quantum systems, with implications that extend from the smallest scales of particle physics to the largest scales of cosmology, and even to our understanding of space and time themselves. The laboratory bench had given way to the globe itself. By the early 2000s, physicists were no longer content to demonstrate quantum entanglement across meters or even kilometers. They dreamed of stretching these mysterious quantum connections across continents and ultimately into space itself. What had begun as tabletop experiments in university basements would soon span oceans and reach toward the stars, transforming our planet into a vast quantum laboratory. The journey from laboratory to global scale began with a simple but profound realization. If quantum entanglement was truly fundamental to nature, it should work regardless of distance. the correlations between entangled particles shouldn't weaken as they separated, no matter whether they were millimeters or megameters apart. But proving this required overcoming extraordinary technical challenges that pushed the boundaries of optical engineering and precision measurement. Anton Zeilinger, the Austrian physicist who had become entanglement's most ambitious explorer, led many of the early long-distance experiments. In the late 1990s, his team achieved entanglement across the Danube River in Vienna, separating their detection stations by 600 meters. This may seem modest by today's standards, but it represented a crucial proof of principle that quantum correlations could survive transmission through the atmosphere over significant distances. The atmospheric challenge was more serious than it might initially appear. Earth's atmosphere is filled with molecules that scatter and absorb light, gradually weakening optical signals as they travel. Turbulence causes additional problems, creating random fluctuations in the refractive index that can distort optical beams and reduce measurement precision. For quantum entanglement experiments that depend on detecting individual photons with perfect timing, these atmospheric effects pose severe limitations. Zeilinger's team developed ingenious solutions to overcome atmospheric interference. They used adaptive optics systems that continuously adjusted their optical components to compensate for atmospheric turbulence. Sophisticated timing systems synchronized their measurements to nanosecond precision, ensuring that they could identify which photons belonged to entangled pairs, even when atmospheric scattering caused random delays. The success of the Danube experiment emboldened researchers to attempt even more ambitious long-distance demonstrations. Teams around the world began establishing entanglement links across harbors, valleys, and mountain ranges. Each successful experiment extended the demonstrated range of quantum correlations and provided valuable experience in dealing with the practical challenges of long-distance quantum communication. One of the most spectacular early achievements came from a collaboration between researchers in the Canary Islands. Using the clear skies and high-altitude observatories of La Palma and Tenerife, they established an entanglement link across 144 kilometers of open ocean. The experiment required extraordinary precision in optical alignment, as the laser beams carrying entangled photons had to traverse the curvature of the Earth while maintaining sufficient intensity to enable single photon detection. These ground-based long-distance experiments revealed both the promise and limitations of terrestrial quantum communication. While quantum entanglement could indeed survive transmission across significant distances, atmospheric absorption and scattering imposed fundamental limits on how far such experiments could be extended. For truly global quantum communication networks, it became clear that space-based systems would be necessary. The transition to space-based quantum experiments represented one of the most audacious technological leaps in the history of physics. The concept was deceptively simple: launch satellites equipped with quantum sources and detectors, then use them to establish entanglement links with ground stations or other satellites. But the engineering challenges were staggering, requiring the development of quantum systems that could operate reliably in the harsh environment of space while maintaining the extraordinary precision necessary for single photon experiments. China emerged as the unexpected leader in space-based quantum research. While European and American teams had pioneered many of the fundamental techniques, Chinese scientists and engineers proved most willing to commit the enormous resources necessary to develop practical space-based quantum systems. Their efforts culminated in 2016 with the launch of Meteus, the world's first quantum science satellite. Named after the ancient Chinese philosopher Mozi, who conducted some of the earliest recorded experiments with light and optics, the Meteus satellite represented a technological tour de force. Weighing 600 kilograms and equipped with sophisticated optical systems, the satellite could generate entangled photon pairs and beam them down to ground stations with remarkable precision. The quantum source at its heart produced millions of entangled photon pairs each second, though only a tiny fraction survived the journey through space and atmosphere to reach ground-based detectors. The satellite's optical system was a marvel of miniaturization and precision engineering. Multiple laser systems created the conditions for entangled photon generation, while precision pointing mechanisms kept the optical beams aligned with ground stations as the satellite raced across the sky at speeds exceeding 25,000 kilometers per hour. Advanced timing systems synchronized the satellite's operations with ground-based equipment, enabling the correlation measurements necessary to verify quantum entanglement. The first results from Messius exceeded even the most optimistic expectations. The satellite successfully established entanglement links with ground stations separated by more than 1,000 kilometers, demonstrating quantum correlations across distances that would have been unimaginable just decades earlier. The measured Bell inequality violations were clear and statistically significant, providing unambiguous evidence that quantum entanglement could survive the journey to space and back. But distance was only one of the remarkable achievements of the Messius mission. The satellite also demonstrated quantum key distribution across continental distances, laying the groundwork for unhackable communication systems that could span the globe. By encoding information in quantum states and using entanglement to detect eavesdropping attempts, the satellite showed how quantum mechanics could provide unprecedented security for sensitive communications. The success of Messius inspired a new generation of space-based quantum experiments. European teams began developing their own quantum satellites, while private companies entered the field with ambitious plans for commercial quantum communication networks. The dream of a global quantum internet, where entangled particles would enable secure communication and distributed quantum computing across the planet, began to seem achievable rather than fantastical. Ground-based experiments also continued to push boundaries, though in different directions. Rather than simply extending distance, researchers began exploring new types of quantum systems and novel applications of long-distance entanglement. Teams demonstrated entanglement between different types of particles, between matter and light, and between quantum systems with vastly different physical properties. One particularly intriguing development was the demonstration of entanglement between atomic systems and photons traveling over fiber optic networks. These experiments showed how quantum information could be stored in stationary atoms while being transmitted through photons, enabling hybrid quantum systems that combined the best features of different physical platforms. Such systems could form the backbone of future quantum networks, where information is processed in atomic quantum computers and transmitted through photonic communication channels. The fiber optic experiments also revealed new challenges and opportunities for terrestrial quantum networks. Unlike free space optical links, fiber optic cables provide protection from atmospheric interference and can maintain stable transmission properties over long distances. However, they also introduce new sources of decoherence and photon loss that must be carefully managed to preserve quantum entanglement. Researchers developed sophisticated techniques for quantum error correction and entanglement purification to overcome the limitations of fiber optic transmission. These methods allow quantum information to be transmitted reliably, even through imperfect channels that introduce noise and losses. By combining multiple noisy entangled states, it's possible to create a smaller number of high-quality entangled pairs that can support quantum communication and computation applications. The development of quantum repeaters represents one of the most important advances in long-distance quantum communication. Just as classical communication networks use repeaters to amplify and retransmit signals over long distances, quantum repeaters can extend the range of quantum entanglement by creating chains of shorter entangled links. However, quantum repeaters are far more complex than their classical counterparts because they must preserve the delicate quantum properties of the transmitted information. Quantum repeaters work by establishing entanglement between adjacent nodes in a communication network then using quantum teleportation to extend entanglement across the entire chain. This process requires quantum memory systems that can store entangled states while waiting for the network synchronization necessary to complete the teleportation protocol. The development of practical quantum memories remains one of the key challenges for large-scale quantum networks. Despite these challenges, prototype quantum repeater networks have been demonstrated in several locations around the world. These early systems show how quantum entanglement can be extended across distances much greater than would be possible with direct transmission, pointing toward future networks that could span continents, or even reach between Earth and space-based quantum systems. The integration of ground-based and space-based quantum systems represents the next frontier in long-distance entanglement research. Hybrid networks that combine the advantages of terrestrial fiber optic links with the global reach of satellite connections could provide the foundation for a truly worldwide quantum internet. Such networks would enable new applications ranging from distributed quantum computing to ultra-secure international communications. Recent experiments have begun to explore these hybrid architectures, demonstrating entanglement distribution between satellites and ground stations connected by fiber optic networks. These experiments show how quantum information can flow seamlessly between different types of physical systems, creating integrated networks that leverage the strengths of each component technology. The military and intelligence communities have taken particular interest in space-based quantum communication systems because of their potential for providing communications that are secure against even the most sophisticated adversaries. Unlike classical encryption methods that depend on mathematical assumptions about computational difficulty, quantum cryptography derives its security from the fundamental laws of physics themselves. Any attempt to intercept quantum encrypted messages inevitably disturbs the quantum states, alerting the legitimate users to the presence of eavesdroppers. However, the development of practical quantum communication systems faces significant economic and technical hurdles. The cost of launching and operating quantum satellites remains extremely high, while the data transmission rates of current systems are far below what would be needed for most practical applications. Ground-based quantum networks face their own challenges, including the need for specialized infrastructure and the difficulty of maintaining quantum coherence over extended distances. Despite these challenges, the pace of progress in long-distance quantum entanglement continues to accelerate. New satellite missions are being planned by multiple countries and private companies, each promising improved performance and new capabilities. Ground-based networks are being extended and connected, creating the beginnings of regional quantum communication infrastructures that could eventually be linked into global systems. The scientific implications of long-distance entanglement experiments extend far beyond their technological applications. By demonstrating quantum correlations across increasingly vast distances, these experiments probe the fundamental nature of space and time themselves. They test whether the laws of quantum mechanics remain valid on astronomical scales, and whether the mysterious connections between entangled particles might play a role in cosmological phenomena. In the summer of 2017, a message traveled from Beijing to Vienna that would have seemed impossible to earlier generations of cryptographers. The communication itself was unremarkable, a simple exchange between research institutions. But the method of transmission represented a revolution in the ancient art of keeping secrets. The message was protected by the laws of quantum mechanics themselves, making it theoretically impossible for any eavesdropper to intercept without detection. This historic exchange marked the first intercontinental quantum key distribution, achieved through a combination of the Chinese Michia satellite and ground stations in both Asia and Europe. The success demonstrated that quantum entanglement could provide not just fascinating physics demonstrations, but practical solutions to one of humanity's oldest challenges: how to communicate sensitive information securely across hostile territory. The concept of quantum cryptography emerged from the recognition that quantum mechanics could revolutionize information security in ways that go far beyond improving existing encryption methods. Traditional cryptography relies on mathematical problems that are difficult for classical computers to solve, such as factoring large numbers or solving discrete logarithm problems. These methods work well today, but they could become vulnerable if more powerful computers are developed or if new mathematical algorithms are discovered. Quantum cryptography takes a fundamentally different approach. Instead of relying on the computational difficulty, it derives its security from the basic principles of quantum mechanics. Any attempt to intercept quantum encrypted messages necessarily disturbs the quantum states carrying the information, leaving detectable traces that alert the legitimate users to the presence of an eavesdropper. This provides what cryptographers call information theoretic security, protection that is guaranteed by the laws of physics rather than assumptions about computational limitations. The most mature application of quantum cryptography is quantum key distribution, often abbreviated as QKD. This technique allows two parties to establish a shared secret key that can be used for conventional encryption of their subsequent communications. The quantum channel is used only to distribute the key, not to transmit the actual message content, but the security of the key distribution process provides unbreakable protection for all communications that use the shared key. The basic principle of quantum key distribution is elegantly simple. Alice, the sender, encodes random bits of information in quantum states and transmits them to Bob, the receiver, through a quantum channel. Bob measures the received quantum states and records his results. Due to the fundamental uncertainty principle of quantum mechanics, Bob's measurements will sometimes give incorrect results, even in the absence of any eavesdropping. But Alice and Bob can identify and discard these errors through classical communication. The crucial insight is that any eavesdropper, traditionally called Eve, who attempts to intercept the quantum states, will inevitably introduce additional errors beyond those caused by quantum uncertainty. Alice and Bob can detect these excess errors by comparing a randomly selected subset of their measurement results through public communication. If the error rate is too high, they know that someone has been eavesdropping and they discard the entire key. If the error rate is acceptably low, they can use the remaining bits as a secure encryption key. The first practical demonstration of quantum key distribution was achieved in 1992 by Charles Bennett and Gilles Brassard, building on theoretical work they had published nearly a decade earlier. Their initial experiment transmitted quantum encrypted keys across 32 centimeters of laboratory space, using polarized photons to encode the secret information. While the distance was modest, the experiment proved that quantum cryptography could work with real hardware rather than just in theoretical papers. Subsequent decades saw dramatic improvements in both the distance and speed of quantum key distribution systems. Laboratory demonstrations gave way to experiments across optical fibers spanning tens and then hundreds of kilometers. Commercial quantum cryptography systems began appearing in the early 2000s, initially serving niche markets where absolute security was worth the high cost and complexity of quantum technology. The development of practical quantum key distribution faced numerous technical challenges that required innovative solutions. Quantum states are extraordinarily fragile, easily disrupted by environmental noise, equipment imperfections, and transmission losses. Real-world quantum cryptography systems must operate reliably despite these imperfections while maintaining their theoretical security guarantees. One of the most significant challenges is the rate at which secret keys can be generated. Early quantum key distribution systems could produce only a few bits per second of verified secret key material, far too slow for protecting high-bandwidth communications. Improving key generation rates required advances in quantum sources, detectors, and signal processing techniques. Photon sources for quantum cryptography must produce single photons on demand with precise timing and well-defined quantum states. This is much more difficult than it might initially appear, because most practical light sources produce multiple photons some of the time, creating security vulnerabilities that sophisticated eavesdroppers might exploit. Researchers developed specialized single-photon sources and protocols that can maintain security even with imperfect photon sources. Similarly, single-photon detectors must register individual photons with high efficiency and low error rates, while operating at the high speeds necessary for practical key distribution. Superconducting nanowire detectors, silicon avalanche photodiodes, and other specialized technologies have been developed to meet these demanding requirements. Each improvement in detector performance translates directly into improved security and higher key generation rates. The transmission of quantum states over long distances presents additional challenges. Optical fibers absorb and scatter photons, limiting the distance over which quantum signals can be transmitted directly. Atmospheric transmission for satellite-based systems faces similar limitations due to absorption and turbulence. These losses not only reduce signal strength, but can create security vulnerabilities if not properly accounted for in the cryptographic protocols. Quantum repeaters offer a potential solution to distance limitations, but practical quantum repeaters remain beyond current technology. Instead, researchers have developed trusted relay systems that can extend the range of quantum key distribution by creating chains of shorter quantum links connected by secure classical processing nodes. While these systems don't provide the same end-to-end security guarantees as true quantum repeaters, they enable quantum-protected communication across much greater distances than would otherwise be possible. The integration of quantum key distribution with existing communication infrastructure requires careful consideration of both security and practical deployment issues. Quantum cryptography systems must interface with conventional networks and security protocols while maintaining their quantum security advantages. This has led to the development of hybrid systems that use quantum key distribution to enhance, rather than replace, existing encryption methods. Financial institutions have emerged as early adopters of quantum cryptography technology, driven by their need to protect high-value transactions and sensitive customer information. Several banks and trading firms have deployed quantum key distribution systems to secure their most critical communications links. While the technology remains expensive and complex, the absolute security guarantees make it attractive for protecting the most valuable information assets. Government and military organizations have also invested heavily in quantum cryptography research and deployment. The potential for quantum computers to break existing encryption methods has created urgency around developing quantum-resistant security technologies. Quantum key distribution offers protection that will remain secure even against future quantum computer attacks, making it particularly attractive for protecting classified information with long-term value. The Chinese government has made particularly aggressive investments in quantum communication infrastructure, deploying quantum key distribution networks across multiple cities and provinces. The Beijing-Shanghai Quantum Communication Backbone, completed in 2017, spans over 2,000 kilometers and connects major population and industrial centers. This network demonstrates the feasibility of large-scale quantum communication infrastructure and provides a testbed for developing practical applications. European initiatives have focused on developing international quantum communication networks that can connect research institutions and government agencies across national borders. The Quantum Internet Alliance and similar programs aim to create a European quantum communication infrastructure that could eventually be extended globally. These efforts face significant technical and political challenges, but represent important steps toward practical quantum communication networks. Private companies have begun entering the quantum cryptography market, developing commercial systems and services that bring quantum security to a broader range of customers. Companies like ID Quantique, MagiIQ Technologies, and Quantum Key Distribution Limited offer turnkey quantum cryptography solutions for organizations that need the highest levels of communication security. However, the commercial quantum cryptography market faces significant barriers to widespread adoption. The high cost of quantum hardware, the complexity of system installation and maintenance, and the limited range of current technology restrict quantum cryptography to niche applications where security requirements justify the expense and complexity. The emergence of quantum hacking has created new challenges for practical quantum cryptography systems. While quantum key distribution is theoretically secure, real-world implementations may contain vulnerabilities that sophisticated attackers can exploit. Researchers have demonstrated attacks on commercial quantum cryptography systems that exploit imperfections in components like single-photon sources and detectors. These attacks have led to the development of device-independent quantum cryptography protocols that can provide security guarantees even when the quantum hardware contains unknown imperfections. Bell inequality violations play a crucial role in these protocols, providing a way to verify that the quantum systems are operating correctly without requiring detailed knowledge of their internal workings. The threat of quantum computers to existing encryption methods has created additional urgency around quantum cryptography deployment. Large-scale quantum computers could break the RSA, elliptic curve, and other cryptographic methods that currently protect most digital communications. While such computers don't yet exist, the possibility that they could be developed within the next few decades has prompted efforts to deploy quantum-resistant security technologies before they become critically needed. Post-quantum cryptography represents an alternative approach to the quantum computer threat, developing new mathematical encryption methods that should remain secure even against quantum computer attacks. These methods could be deployed more easily and cheaply than quantum cryptography, but they still rely on computational assumptions that could potentially be overturned by new mathematical discoveries or algorithmic advances. The combination of post-quantum cryptography and quantum key distribution could provide multiple layers of protection against future security threats. Even if one layer is compromised, the other could maintain communication security. This defense-in-depth approach is particularly attractive for protecting the most sensitive information that must remain secure for many years. The development of quantum communication networks is also driving advances in quantum networking protocols and quantum internet architectures. Researchers are developing techniques for routing quantum information through multi-node networks, establishing entanglement between arbitrary network nodes, and supporting multiple users and applications simultaneously. Quantum network protocols must address unique challenges that don't exist in classical networks. Quantum information cannot be copied, making error correction and network redundancy much more difficult. Quantum states are fragile and can be destroyed by measurement, requiring new approaches to network monitoring and management. The no-cloning theorem prohibits many classical networking techniques like packet duplication and broadcast communication. Despite these challenges, prototype quantum networks have been demonstrated in several locations around the world. These experimental networks provide testbeds for developing quantum networking technologies and exploring potential applications beyond simple key distribution. Future quantum networks could support distributed quantum computing, quantum-enhanced sensing networks, and other applications that leverage the unique properties of quantum entanglement. In a gleaming laboratory nestled in the hills of Santa Barbara, engineers at Google were making final preparations for what they hoped would be a historic moment. The year was 2019, and their quantum computer, dubbed Sycamore, was about to attempt something that classical computers considered impossible. The machine contained 53 quantum bits, or qubits, each capable of existing in superposition states that defied classical logic. But the true power of Sycamore lay not in its individual qubits, but in the intricate web of quantum entanglement that connected them into a unified quantum system. The task that Google set for Sycamore seemed deceptively simple. Sample the output of a specific quantum circuit, faster than the world's most powerful classical supercomputers, could simulate the same process. This quantum sampling problem had no practical application, but it served as a carefully designed benchmark that highlighted the fundamental differences between quantum and classical computation. Success would mark the achievement of quantum supremacy, the first demonstration that quantum computers could outperform classical machines on any task. When Sycamore completed its calculation in just over 3 minutes, producing a result that would have taken classical computers thousands of years to verify, it marked a watershed moment in the history of computation. But the achievement rested entirely on quantum entanglement's ability to create computational states that are impossible to simulate efficiently on classical machines. Without entanglement, Sycamore would have been nothing more than an expensive classical computer operating in an unnecessarily complicated way. The story of quantum computing begins with a profound insight about the relationship between physics and computation. In the early 1980s, physicist Richard Feynman observed that classical computers struggle to simulate quantum mechanical systems because the amount of information needed to describe a quantum system grows exponentially with the number of particles involved. A classical computer trying to simulate 50 qubits would need to track more than a quadrillion possible quantum states simultaneously, quickly overwhelming even the most powerful machines. Feynman's insight was that quantum computers could sidestep this exponential scaling problem by using quantum systems to simulate other quantum systems directly. Instead of trying to calculate what a quantum system would do, you could simply build an analogous quantum system and observe its behavior. This approach promised not just incremental improvements in computational speed, but qualitative breakthroughs that could solve problems considered intractable for classical machines. The key to quantum computing's potential lies in the phenomenon of quantum superposition, which allows qubits to exist in combinations of 0 and 1 simultaneously, while a classical bit must be either 0 or 1 at any given moment. A qubit can be in any quantum superposition of these states until measured. This means that n qubits can represent up to 2 to the power of n different states simultaneously, providing exponential scaling in computational capacity. But superposition alone is not sufficient for quantum computational advantage. Individual qubits in superposition can be simulated efficiently on classical computers, and many quantum algorithms that use only superposition without entanglement can be replicated classically. The true power of quantum computing emerges when qubits become entangled, creating quantum states that cannot be factored into independent components. Entanglement transforms a collection of individual qubits into a unified quantum system whose behavior cannot be predicted by analyzing its components separately. When qubits are entangled, measuring one qubit instantaneously affects the quantum states of all its entangled partners, regardless of their physical separation within the quantum computer. This non-local connectivity allows quantum algorithms to perform parallel operations across the entire quantum state space in ways that classical computers cannot replicate efficiently. The mathematical description of entangled quantum states reveals why they are so computationally powerful. While n classical bits require n numbers to specify their state completely, n entangled qubits require up to 2 to the power of n complex numbers for their full quantum description. This exponential scaling in the amount of information needed to characterize quantum states is what makes quantum systems so difficult to simulate classically and so powerful for certain computational tasks. Quantum algorithms exploit entanglement in sophisticated ways to achieve computational speedups over classical methods. Shor's algorithm for factoring large integers uses entanglement to create quantum superpositions that encode information about all possible factors simultaneously. Grover's algorithm for searching unstructured databases uses entanglement to amplify the probability of finding the correct answer while suppressing incorrect possibilities. In both cases, The quantum speedup depends critically on maintaining and manipulating entangled states throughout the computation. The physical implementation of quantum computers requires exquisite control over quantum entanglement generation and manipulation. Different technological approaches use various physical systems as qubits, including superconducting circuits, trapped ions, photons, and semiconductor quantum dots. Each platform has unique advantages and challenges, but all must solve the fundamental problem of creating controllable entanglement between qubits while protecting these fragile quantum states from environmental interference. Superconducting quantum computers, like Google's Sycamore and IBM's quantum systems, use tiny circuits made from materials that conduct electricity without resistance at extremely low temperatures. These circuits can be designed to behave like artificial atoms with discrete energy levels that serve as qubit states. Superconducting qubits can be entangled by allowing them to interact through carefully engineered coupling elements that create controlled quantum interactions. The advantage of superconducting qubits lies in their fast operation speeds and the mature semiconductor fabrication techniques that can be adapted for their production. However, they require dilution refrigerators that cool the quantum processes to temperatures colder than outer space, making the systems large and expensive. The superconducting qubits are also relatively short-lived, maintaining their quantum properties for only tens of microseconds before decoherence destroys their quantum states. Trapped ion quantum computers take a radically different approach, using electrically charged atoms suspended in electromagnetic fields as qubits. The internal electronic states of the ions serve as qubit levels, while entanglement is created through their shared vibrational motion in the ion trap. Laser pulses provide precise control over individual qubits and can create entangling interactions between any pair of ions in the trap. Trapped ion systems offer several advantages over superconducting approaches. The ions are identical quantum systems provided by nature, eliminating manufacturing variations that plague artificial qubits. They can maintain quantum coherence for much longer periods, sometimes several minutes rather than microseconds. However, trapped ion operations are typically slower than superconducting systems, and scaling to large numbers of qubits presents significant engineering challenges. Photonic quantum computers use individual particles of light as qubits, encoding quantum information in properties like photon polarization or path. Entanglement between photonic qubits can be created using optical elements like beam splitters and phase shifters. While photonic systems naturally operate at room temperature and can transmit quantum information over long distances, they face challenges in creating the strong interactions between photons necessary for universal quantum computation. Regardless of the physical implementation, all quantum computers must grapple with the fundamental challenge of decoherence, the process by which quantum systems lose their coherent superposition and entanglement due to unwanted interactions with their environment. Decoherence is the arch enemy of quantum computation, gradually corrupting quantum information and destroying the entangled states that provide quantum computational advantage. The timescale for decoherence varies dramatically between different quantum computing platforms and depends critically on how well the qubits can be isolated from environmental disturbances. Factors like temperature, electromagnetic fields, mechanical vibrations, and even cosmic rays can contribute to decoherence and limit the complexity of quantum computations that can be performed reliably. Quantum error correction represents the most ambitious approach to overcoming decoherence limitations. By encoding each logical qubit in multiple physical qubits and using sophisticated error detection and correction protocols, quantum computers could potentially perform arbitrarily long computations despite ongoing decoherence of individual physical qubits. However, quantum error correction requires enormous overhead, with estimates suggesting that hundreds or thousands of physical qubits may be needed to create a single error corrected logical qubit. Current quantum computers operate in what researchers call the noisy intermediate scale quantum, or NISQ era. These devices contain enough qubits to demonstrate quantum computational advantages for specific problems, but lack the error correction capabilities needed for general-purpose quantum computation. NISQ devices must complete their computations before decoherence destroys the quantum states, limiting them to relatively shallow quantum circuits with modest numbers of operations. Despite these limitations, NISQ quantum computers have begun demonstrating practical applications in areas like quantum chemistry simulations, optimization problems, and machine learning. These applications typically don't require the full power of fault-tolerant quantum computation, but can benefit from the unique capabilities of entangled quantum systems to explore solution spaces that are inaccessible to classical computers. Quantum chemistry simulations represent one of the most promising near-term applications for quantum computers. Molecules are inherently quantum mechanical systems whose properties depend on the complex entanglement patterns of their constituent electrons. Classical computers struggle to simulate large molecules accurately because the quantum many-body problem scales exponentially with system size. Quantum computers could potentially simulate molecular systems directly, enabling the design of new materials, catalysts, and pharmaceuticals. Early demonstrations of quantum chemistry simulations have shown promise, though current systems are limited to very small molecules. IBM's quantum computers have simulated simple molecules like hydrogen and lithium hydride, while Google's Sycamore has tackled slightly larger systems. These proof-of-principle demonstrations point toward future applications where quantum computers could revolutionize drug discovery and materials science. Optimization problems represent another area where quantum computers might provide near-term advantages. Many important optimization challenges, from logistics planning to financial portfolio optimization, involve searching through enormous solution spaces for optimal configurations. Quantum algorithms like the Quantum Approximate Optimization Algorithm, or QAOA, use entanglement to explore multiple solution candidates simultaneously, potentially finding better solutions faster than classical methods. The development of quantum machine learning algorithms has created additional opportunities for quantum computational advantage. Some machine learning problems involve high-dimensional vector spaces and complex correlation patterns that might be naturally suited to quantum computational approaches. Quantum computers could potentially recognize patterns in data or optimize machine learning models in ways that leverage the unique properties of entangled quantum states. However, determining exactly where quantum computers will provide practical advantages remains an active area of research. Many problems that initially seemed well suited to quantum acceleration have turned out to be solvable efficiently on classical computers using improved algorithms or specialized hardware. The search for quantum computational advantage requires careful analysis of both quantum and classical approaches to ensure that quantum speedups are genuine rather than artifacts of comparing optimized quantum algorithms to suboptimal classical methods. The race to build larger and more capable quantum computers has intensified dramatically in recent years. IBM has announced plans to build quantum computers with thousands of qubits by the end of the decade, while Google, Amazon, and Microsoft have launched major quantum computing initiatives. Startups like Rigetti Computing, IonQ, and PsiQuantum are pursuing alternative approaches that could lead to breakthroughs in quantum hardware development. The competition has also sparked international efforts to develop quantum computing capabilities. China has invested billions of dollars in quantum research and has achieved several important milestones, including demonstrations of quantum computational advantage using photonic systems. The European Union has launched a quantum flagship program to coordinate research across member countries, while countries like Canada, Australia, and Japan have established national quantum computing programs. Despite the intense competition and massive investments, significant challenges remain before quantum computers can tackle the most important computational problems. Scaling quantum systems to millions of qubits while maintaining low error rates represents an enormous engineering challenge. Developing quantum algorithms that provide clear advantages over classical methods for practically important problems requires continued research at the intersection of computer science, physics, and mathematics. The integration of quantum computers with classical computing infrastructure also presents important challenges and opportunities. Hybrid quantum classical algorithms that combine the strengths of both computational paradigms may prove more practical than purely quantum approaches for many applications. This integration requires developing new programming languages, software tools, and system architectures that can manage the complex interactions between quantum and classical processing elements. The experimental evidence was overwhelming. Decades of increasingly sophisticated tests had confirmed beyond reasonable doubt that quantum entanglement was real, that Bell's inequality was indeed violated in nature, and that the universe operated according to principles that defied classical intuition. Yet even as physicists celebrated these experimental triumphs, a deeper question remained stubbornly unanswered. What did quantum entanglement actually tell us about the nature of reality itself? The resolution of the EPR paradox had not brought philosophical closure, but had instead opened new chasms of conceptual difficulty. Einstein's dream of a classical, deterministic universe governed by local interactions had been shattered by experimental results. But what would replace it? How should we understand a world where distant particles remained mysteriously connected, where measurements seemed to create rather than reveal properties, and where the act of observation played such a fundamental role in determining physical outcomes? The Copenhagen interpretation, developed by Bohr and his colleagues in the 1920s, had provided the standard framework for understanding quantum mechanics for nearly a century. According to this view, quantum systems exist in superposition states until measured, at which point the wave function collapses and definite properties emerge. The interpretation treats measurement as a fundamental process that cannot be reduced to more basic physical interactions, and it assigns no physical reality to quantum states themselves, viewing them merely as tools for calculating measurement probabilities. For many physicists, the Copenhagen interpretation offered a pragmatic solution to the conceptual puzzles of quantum mechanics. It provided clear rules for calculating experimental outcomes and had proven remarkably successful in predicting the results of countless experiments. The interpretation avoided philosophical complications by focusing on what could be measured rather than speculating about underlying reality. But the demonstration of quantum entanglement and the violation of Bell's inequality forced physicists to confront the conceptual foundations of quantum mechanics more directly. If entangled particles really could affect each other instantaneously across vast distances, what did this mean for our understanding of space, time, and causality? If measurement truly created rather than revealed particle properties, how should we understand the relationship between observers and the physical world? The many worlds interpretation, originally proposed by Hugh Everett in 1957 and later championed by physicists like David Deutsch and Max Tegmark, offered a radically different perspective on these questions. According to this interpretation, quantum superposition never actually collapses. Instead, each possible measurement outcome occurs in a separate branch of reality, creating a vast multiverse where every quantum possibility is realized somewhere. In the many worlds picture, entanglement correlations arise because measurement processes cause the universe to branch in coordinated ways across all parts of an entangled system. When you measure one particle of an entangled pair and observe it spinning clockwise, the universe splits into multiple branches. In every branch where your particle spins clockwise, its distant partner spins counterclockwise, ensuring perfect correlations without requiring any instantaneous influence between the particles. The many worlds interpretation eliminates the need for wave function collapse and restores determinism to quantum mechanics, albeit at the cost of postulating an infinite number of parallel universes. Every quantum measurement splits reality into countless branches, most of which become permanently inaccessible to each other. The interpretation suggests that you are constantly branching into multiple copies of yourself, each experiencing a different sequence of measurement outcomes in their respective universal branches. While many worlds avoid some conceptual problems of the Copenhagen interpretation, it raises profound questions of its own. If parallel universes exist but can never be observed or contacted, do they have any meaningful physical reality? How should we understand probability in a deterministic theory where every possible outcome actually occurs? And what does personal identity mean if countless copies of yourself exist across different branches of the multiverse? De Broglie-Bohm theory, also known as pilot wave theory, represents yet another approach to understanding quantum mechanics and entanglement. Originally proposed by Louis de Broglie in 1927 and later developed by David Bohm in 1952, this interpretation maintains that particles always have definite positions and velocities, contrary to the Copenhagen view. However, particles are guided by a quantum wave that determines their motion in ways that can appear random and non-local. In pilot wave theory, entanglement arises because the quantum waves guiding different particles can become correlated, creating coordinated motion that appears to involve instantaneous action at a distance. The theory reproduces all the predictions of standard quantum mechanics while maintaining a deterministic, realist picture of particle behavior. However, it requires accepting that the quantum wave can influence particle motion non-locally, violating the spirit, if not the letter of relativity. The pilot wave approach has attracted renewed interest in recent years as physicists have developed more sophisticated ways to test different interpretations of quantum mechanics. Some researchers hope that future experiments might distinguish between pilot wave theory and other interpretations, though such tests remain technically challenging and conceptually controversial. Other interpretations of quantum mechanics offer additional perspectives on the meaning of entanglement. The relational interpretation, developed by Carlo Rovelli and others, suggests that quantum properties exist only in relation to specific observers, rather than as absolute features of physical systems. According to this view, entanglement correlations arise because different observers share relational information about quantum systems, not because the systems possess intrinsic non-local connections. The consistent histories interpretation, advocated by Murray Gell-Mann, James Hartle, and Robert Griffiths, attempts to apply quantum mechanics to entire cosmological histories rather than just laboratory measurements. This approach treats the universe itself as a quantum system and uses decoherence to explain why we observe apparently classical behavior in macroscopic systems. Entanglement plays a crucial role in determining which histories are consistent and can be assigned meaningful probabilities. Cubism, short for quantum Bayesianism, represents one of the most radical reinterpretations of quantum mechanics. Developed by Christopher Fuchs and others, Cubism treats quantum states as subjective degrees of belief rather than objective features of physical systems. According to this view, entanglement correlations reflect the updating of personal beliefs based on measurement outcomes rather than mysterious connections between distant particles. While these various interpretations differ dramatically in their conceptual frameworks, they all agree on the experimental predictions of quantum mechanics. This remarkable situation, where multiple incompatible worldviews make identical empirical predictions, highlights both the success and the limitations of experimental science in resolving fundamental questions about reality. The philosophical implications of quantum entanglement extend far beyond the narrow question of which interpretation of quantum mechanics is correct. The phenomenon challenges basic assumptions about the nature of scientific explanation, the relationship between observers and the observed world, and the possibility of objective knowledge about physical reality. The violation of Bell's inequality demonstrates that any complete description of physical reality must abandon either locality or realism, the assumption that objects possess definite properties independent of observation. Most physicists have chosen to abandon realism while preserving locality, accepting that measurement creates rather than reveals properties. But this choice has profound implications for how we understand the scientific enterprise itself. If measurement creates properties rather than revealing them, what sense does it make to speak of objective scientific truth? How can science claim to discover facts about the world if those facts depend on the acts of observation that supposedly reveal them? These questions touch on fundamental issues in the philosophy of science that extend far beyond quantum mechanics. The role of consciousness in quantum mechanics has been particularly controversial since the early days of the theory. Some interpretations, like the von Neumann-Wigner interpretation, suggest that conscious observation plays a special role in collapsing quantum wave functions. However, most modern physicists reject the idea that consciousness is necessary for quantum measurement, preferring explanations based on decoherence and environmental interaction. Nevertheless, quantum entanglement has inspired speculation about possible connections between quantum mechanics and consciousness. Some researchers have proposed that quantum effects in the brain might explain aspects of consciousness, free will, or subjective experience. While these ideas remain highly speculative and lack convincing empirical support, they illustrate how quantum mechanics continues to influence thinking about fundamental questions in neuroscience and philosophy of mind. The phenomenon of entanglement has also raised questions about the nature of space and time themselves. Einstein's relativity showed that space and time are intimately connected and can be curved by matter and energy. Quantum entanglement suggests that space might not be as fundamental as classical physics assumed, since entangled particles can remain connected regardless of their spatial separation. Some theoretical physicists have proposed that space itself might emerge from more fundamental quantum entanglement relationships. According to these ideas, the familiar three-dimensional space of everyday experience could be a higher-level description that emerges from underlying quantum correlations, much as temperature emerges from molecular motion without being a fundamental property of individual molecules. The holographic principle, inspired by studies of black holes and string theory, suggests that all the information in a volume of space can be encoded on its boundary surface. Some versions of this principle rely heavily on quantum entanglement to explain how information can be distributed across spatial boundaries. If these ideas are correct, entanglement might play a fundamental role in determining the structure of space and time themselves. Quantum entanglement has also influenced thinking about the nature of information and computation. The phenomenon demonstrates that quantum systems can process and store information in ways that differ qualitatively from classical information processing. This has led to new fields like quantum information theory and quantum computation, which explore how quantum correlations can be exploited for practical applications. The study of entanglement has revealed deep connections between physics and information theory that were not apparent in classical physics. Concepts like entropy, which originated in thermodynamics, have been generalized to describe quantum information and entanglement. These connections suggest that information might be as fundamental to physics as energy and matter, potentially requiring a complete rethinking of how we understand physical reality. The measurement problem in quantum mechanics remains one of the most challenging conceptual issues in modern physics. Despite decades of experimental progress in demonstrating and exploiting quantum entanglement, physicists still lack a complete understanding of how quantum measurements work and why they produce definite outcomes from superposition states. Various approaches to the measurement problem offer different perspectives on how macroscopic measurement devices can extract definite information from quantum systems. Decoherence theory explains how environmental interactions can suppress quantum superpositions, but it doesn't fully explain why specific measurement outcomes are selected. The emergence of classicality from quantum mechanics remains an active area of research that could significantly impact our understanding of entanglement and quantum mechanics more generally. As experimental techniques continue to improve and new applications of quantum entanglement are developed, the philosophical questions surrounding quantum mechanics are likely to evolve as well. Future experiments might provide new insights into the nature of quantum measurement, the boundary between quantum and classical behavior, or the fundamental structure of space and time. However, it's also possible that these philosophical questions will remain unresolved, representing permanent limitations on human understanding of physical reality rather than temporary gaps in scientific knowledge. At the edge of the known universe, where matter spirals into regions of such extreme gravity that space and time themselves begin to break down, quantum entanglement might play its most dramatic and mysterious role. The recent detection of gravitational waves from colliding black holes has opened new windows into these extreme environments, where Einstein's relativity meets quantum mechanics in ways that challenge our deepest understanding of physical reality. Here, in the most violent and exotic corners of the cosmos, entanglement might hold keys to resolving some of the most profound puzzles in modern physics. The journey into extreme physics begins with black holes. Those enigmatic objects where gravity has become so strong that nothing, not even light, can escape once it crosses the event horizon. For decades, black holes seem to represent the ultimate triumph of classical general relativity, where Einstein's geometric description of gravity reaches its most extreme expression. But when physicists began applying quantum mechanics to black holes, they discovered puzzles that continue to confound the brightest minds in theoretical physics. The story started in 1974 when Stephen Hawking made a startling discovery that would forever change how physicists think about black holes. Using techniques from quantum field theory, Hawking showed that black holes should emit radiation and gradually evaporate. This result was shocking because it suggested that black holes, supposedly the ultimate gravitational traps, could actually leak energy and eventually disappear entirely. Hawking radiation arises from quantum fluctuations near the black hole's event horizon. In the vacuum of space, particle-antiparticle pairs constantly appear and disappear due to quantum uncertainty. Near a black hole, these virtual particles can become real if one falls into the black hole while the other escapes. The escaping particle becomes Hawking radiation, while the black hole loses a tiny amount of mass equal to the energy of the particle that fell in. This process seemed straightforward until physicists realized it led to a fundamental paradox. In quantum mechanics, information cannot be destroyed. If you throw a book into a fire, the information in the book is preserved in the arrangement of ash particles and heat radiation, even if it's practically impossible to reconstruct. But Hawking radiation appears to be completely random, carrying no information about what fell into the black hole. If the black hole eventually evaporates completely, the information about everything that ever fell in would be permanently lost, violating one of the most basic principles of quantum mechanics. The black hole information paradox has motivated decades of research into the intersection of quantum mechanics and gravity. Various solutions have been proposed, many involving quantum entanglement in exotic and counterintuitive ways. Some physicists suggest that information is encoded in subtle correlations within Hawking radiation that become apparent only when the entire evaporation process is complete. Others propose that information never really enters the black hole, but becomes encoded on its surface through holographic principles. The holographic principle emerged from studies of black holes and represents one of the most revolutionary ideas in modern theoretical physics. The principle suggests that all the information in a volume of space can be encoded on its boundary surface, like a hologram that creates three-dimensional images from two-dimensional information. For black holes, this means that everything that falls in might actually be encoded on the event horizon surface rather than disappearing into the interior. String theory, humanity's most ambitious attempt to unify quantum mechanics and gravity, has provided additional insights into the role of entanglement in extreme physics. In string theory, fundamental particles are not point-like objects, but tiny vibrating strings existing in higher dimensional spaces. The theory naturally incorporates both quantum mechanics and gravity, potentially resolving many of the conceptual difficulties that arise when these theories are combined. One of string theory's most intriguing predictions involves the relationship between quantum entanglement and the geometry of space-time itself. The ADS-CFT correspondence, discovered by Juan Maldacena in 1997, establishes a precise mathematical relationship between gravity in higher dimensional spaces and quantum field theories without gravity in lower dimensional boundaries. This correspondence suggests that gravity and space-time geometry might emerge from quantum entanglement patterns in more fundamental quantum theories. The ADS-CFT correspondence has led to remarkable insights about the nature of space and time. In this framework, the geometry of space-time is not fundamental, but emerges from entanglement relationships between quantum degrees of freedom living on the boundary of space. When boundary regions become highly entangled, they correspond to smoothly connected regions of the interior space-time. When entanglement is reduced, the corresponding space-time regions become disconnected. This connection between entanglement and geometry has inspired the ER equals EPR conjecture, proposed by Leonard Susskind and Juan Maldacena. The conjecture suggests that quantum entanglement between distant particles might be geometrically equivalent to wormholes connecting distant regions of space-time. In this view, Einstein's spooky action at a distance is not mysterious non-local influence, but rather reflects the hidden geometric connections that link entangled systems through higher dimensional space. If ER equals EPR is correct, then every pair of entangled particles is connected by a microscopic wormhole that exists in dimensions beyond our ordinary three-dimensional space. These wormholes would be far too small to allow travel or communication, but they would provide a geometric interpretation of quantum correlations that preserves locality at a deeper level than apparent in ordinary space-time. The conjecture offers a potential resolution to the black hole information paradox. When particles fall into a black hole, they might become entangled with particles that previously fell in, creating wormhole connections that allow information to eventually escape through Hawking radiation. The process would take enormous amounts of time, but it would preserve the fundamental quantum mechanical principle that information cannot be destroyed. Quantum error correction has emerged as another crucial concept for understanding entanglement in extreme physics. Just as quantum computers use error correction to protect quantum information from decoherence, space-time itself might use similar principles to maintain the integrity of quantum information under extreme conditions. Some researchers suggest that the holographic principle naturally incorporates quantum error correction, with the boundary theory serving as an error-corrected encoding of bulk gravitational physics. These ideas have led to new perspectives on the nature of space-time emergence. Instead of viewing space and time as fundamental aspects of reality, physicists increasingly consider them as emergent properties that arise from more fundamental quantum information processing. In this view, the smooth geometry of general relativity emerges only when quantum error correction successfully protects the underlying quantum information from degradation. The study of black hole interiors has revealed additional connections between entanglement and extreme physics. According to general relativity, observers falling into black holes should experience smooth space-time as they cross the event horizon, encountering no local signs that they have entered a region from which escape is impossible. However, quantum mechanics suggests that the black hole interior might be much more complex and exotic than classical relativity predicts. The firewall paradox, identified by Ahmed Almheiri and colleagues in 2012, highlights potential conflicts between general relativity and quantum mechanics at black hole horizons. If information must escape from black holes to preserve quantum mechanics, then the smooth spacetime predicted by relativity might be replaced by a violent firewall that destroys anything attempting to cross the event horizon. This paradox remains unresolved and continues to drive research into the fundamental nature of spacetime and gravity. Experimental tests of these exotic ideas remain challenging because the relevant physics occurs in environments that are inaccessible to direct observation. However, advances in gravitational wave astronomy have begun providing new windows into extreme gravitational environments. The Laser Interferometer, Gravitational Wave Observatory, or LIGO, and similar detectors have observed dozens of black hole mergers, each providing information about how spacetime behaves under the most extreme conditions in the universe. These observations have confirmed many predictions of general relativity in the strong field regime, but they have also opened possibilities for testing quantum gravitational effects. Future gravitational wave detectors might be sensitive enough to observe subtle quantum effects in black hole mergers, or to detect signatures of exotic spacetime structures predicted by theories that incorporate quantum entanglement. The connection between entanglement and spacetime has also influenced cosmology, the study of the universe as a whole. Some cosmological models suggest that quantum entanglement played a crucial role in the early universe, potentially explaining the observed properties of cosmic microwave background radiation and the large-scale structure of the universe. Inflation, the theory that the universe underwent exponential expansion in its earliest moments, naturally creates quantum entanglement between different regions of space. During inflation, quantum fluctuations that start smaller than atoms are stretched to cosmic scales, creating the seeds that eventually grow into galaxies and galaxy clusters. The quantum correlations established during inflation might be detectable in the cosmic microwave background, providing observational evidence for quantum effects in cosmology. The multiverse concept, which suggests that our observable universe is just one of many universes in a vast cosmic ensemble, also relies heavily on quantum mechanics and entanglement. In eternal inflation models, quantum fluctuations continuously create new universe regions with different physical properties. The branching structure of the multiverse resembles the many worlds interpretation of quantum mechanics, with each universe branch representing a different realization of quantum possibilities. Dark energy, the mysterious force driving the accelerated expansion of the universe, might also have connections to quantum entanglement. Some theoretical models suggest that dark energy arises from quantum vacuum fluctuations, or from entanglement between different regions of spacetime. While these ideas remain highly speculative, they illustrate how quantum entanglement might play fundamental roles in cosmological phenomena. The emergence of spacetime from quantum entanglement has profound implications for our understanding of the arrow of time. In fundamental physics, most equations are symmetric under time reversal, providing no explanation for why time appears to flow in a preferred direction. However, entanglement naturally breaks time reversal symmetry through the process of decoherence, potentially explaining why we experience time as flowing from past to future. Quantum entanglement might also provide insights into the nature of consciousness and its relationship to physical reality. Some researchers have speculated that conscious experience emerges from quantum entanglement patterns in the brain, though these ideas remain highly controversial and lack convincing experimental support. Nevertheless, the connection between entanglement and information processing continues to inspire new approaches to understanding consciousness and its place in the physical world. The search for a complete theory of quantum gravity remains one of the greatest challenges in modern physics. String theory, loop quantum gravity, causal dynamical triangulation, and other approaches all attempt to reconcile quantum mechanics with general relativity, but none has yet achieved complete success. Quantum entanglement appears to play crucial roles in all these approaches, suggesting that understanding entanglement might be the key to unlocking the deepest secrets of space, time, and gravity. As experimental techniques continue to advance and theoretical insights deepen, the role of quantum entanglement in extreme physics will likely become clearer. Future observations of black holes, gravitational waves, and cosmological phenomena might provide direct evidence for the exotic quantum effects predicted by current theories. Alternatively, new discoveries might force physicists to completely revise their understanding of how quantum mechanics and gravity interact in extreme environments. The journey from Bell's theorem to black hole physics illustrates how fundamental insights about quantum entanglement continue to reshape our understanding of physical reality. What began as an abstract philosophical debate about the completeness of quantum mechanics has evolved into a research program that touches the deepest questions about the nature of space, time, and existence itself. As we stand at the threshold of a new era in physics, looking back across nearly a century of discovery and debate, the story of quantum entanglement reads like humanity's most profound detective story. What began with Einstein's uncomfortable intuition about spooky action at a distance has evolved into a fundamental principle that touches every corner of modern physics, from the smallest scales of quantum mechanics to the largest scales of cosmology. The journey has transformed our understanding not just of how particles behave, but of the very nature of reality itself. The experimental evidence is now overwhelming and undeniable. Bell's inequality is violated in nature with extraordinary precision and consistency. Quantum entanglement is real, producing correlations between distant particles that cannot be explained by any theory respecting both locality and realism. The Nobel Prize recognition of Aspect, Clauser, and Zeilinger in 2022 marked not just the culmination of decades of experimental work, but the definitive settlement of a debate that had raged since the birth of quantum mechanics. Yet the resolution of the empirical questions has only deepened the conceptual mysteries. We know with certainty that entangled particles exhibit correlations that violate classical expectations, but we still struggle to understand what this tells us about the fundamental nature of space, time, and existence. The various interpretations of quantum mechanics offer different frameworks for understanding entanglement, but none provides a complete picture that satisfies all physicists or resolves all conceptual difficulties. What has emerged with startling clarity is that quantum entanglement is not merely a curious side effect of quantum mechanics, but appears to be one of the most fundamental features of physical reality. Entanglement enables quantum computing, secures quantum communication, and might even underlie the emergence of space and time themselves. Far from being an abstract philosophical curiosity, entanglement has become the foundation for revolutionary technologies that promise to transform how we process information, communicate across vast distances, and probe the deepest secrets of nature. The technological applications of quantum entanglement are only beginning to be realized. Quantum computers, still in their infancy, have already demonstrated computational capabilities that exceed classical machines for specialized tasks. As these devices mature and scale to larger numbers of qubits, they could revolutionize fields ranging from drug discovery to cryptography to artificial intelligence. The quantum internet, enabled by entanglement distribution across global networks, could provide unprecedented security for communications and enable distributed quantum computing across continents. But perhaps more important than any specific application is what entanglement has taught us about the interconnected nature of reality. The phenomenon reveals that the universe is not composed of independent, isolated objects, but rather consists of a vast web of quantum correlations that link distant regions in ways that transcend our classical intuitions about space and time. Particles that have never directly interacted can share quantum states that make their behaviors perfectly correlated across arbitrary distances. This interconnectedness suggests that the classical picture of reality, where objects exist independently and influence each other only through local interactions, fundamentally misrepresents the nature of the physical world. Instead, we appear to live in a universe where quantum information and correlations are more fundamental than matter and energy, where the act of measurement plays a creative rather than merely revelatory role, and where the boundaries between observer and observed are far more subtle than classical physics assumed. The implications extend far beyond physics itself. If entanglement reveals something fundamental about the nature of reality, it might inform our understanding of consciousness, free will, and the relationship between mind and matter. While speculative connections between quantum mechanics and consciousness remain controversial and largely unproven, the phenomenon of entanglement demonstrates that reality operates according to principles that are far stranger and more subtle than our everyday experience suggests. The journey from the EPR paradox to modern quantum technologies illustrates how fundamental research into the nature of reality can lead to practical applications that transform human civilization. Einstein's objections to quantum mechanics, motivated by deep philosophical concerns about the completeness of physical theories, ultimately inspired experimental programs that have not only settled those philosophical questions, but have also laid the groundwork for quantum technologies that could reshape the 21st century. This pattern, where fundamental research into abstract questions yields unexpected practical benefits, reflects a deeper truth about the relationship between scientific understanding and technological progress. The most transformative technologies often emerge not from directed efforts to solve practical problems, but from attempts to understand the fundamental principles underlying natural phenomena. The laser, the transistor, and nuclear energy all emerged from basic research into atomic and molecular physics that seemed purely academic at the time. Quantum entanglement represents perhaps the most striking example of this phenomenon. The abstract philosophical debates of the 1930s and the esoteric experimental tests of the 1970s and 80s have given birth to technologies that promise to transform computing, communication, and scientific measurement in the coming decades. The quantum revolution, built on the foundation of entanglement, is still in its earliest stages. Looking toward the future, several profound questions remain unanswered. Will we eventually develop a complete theory of quantum gravity that explains how entanglement relates to the structure of space-time? Can we scale quantum computers to sizes that enable them to solve the most important computational problems facing humanity? Will quantum communication networks eventually span the solar system, enabling instantaneous coordination of activities across interplanetary distances? Perhaps most intriguingly, will we discover that entanglement plays fundamental roles in biological systems, potentially explaining aspects of photosynthesis, avian navigation, or even consciousness itself? Recent research has begun to uncover quantum effects in biological systems that seemed too warm and noisy to support quantum coherence, suggesting that life might have evolved sophisticated mechanisms for exploiting quantum phenomena. The search for extraterrestrial intelligence might also be transformed by our understanding of quantum entanglement. Advanced civilizations might use quantum communication networks that are invisible to classical detection methods, but could be revealed through careful study of quantum correlations. The universe might be crisscrossed with quantum communication channels carrying information between distant civilizations in ways that we are only beginning to imagine. As we peer deeper into the cosmos with increasingly sophisticated instruments, we continue to discover new phenomena that challenge our understanding of physics. Dark matter and dark energy, which together comprise 95% of the universe, remain mysterious despite decades of research. Black holes continue to reveal new puzzles about the nature of space and time. The emergence of complexity and life from simple physical laws raises profound questions about the relationship between physics and biology. Quantum entanglement might hold keys to understanding all of these mysteries. If space-time itself emerges from quantum entanglement, then understanding entanglement might be essential for comprehending dark energy and the accelerated expansion of the universe. If black holes preserve information through quantum correlations, then entanglement might resolve the information paradox and reveal new principles of quantum gravity. If biological systems exploit quantum coherence, then entanglement might bridge the gap between physics and biology in unexpected ways. The story of quantum entanglement also illustrates the power of human curiosity and persistence in the face of seemingly impossible questions. From Einstein's initial discomfort with quantum non-locality, to Bell's brilliant theoretical insights, to the decades of experimental work required to test those insights definitively, the journey has required contributions from multiple generations of physicists who refuse to accept easy answers to deep questions. This collaborative, multi-generational effort reflects one of humanity's greatest strengths: our ability to build knowledge cumulatively across individuals and across time. Each generation of scientists builds on the work of their predecessors, gradually constructing an understanding of nature that no individual could achieve alone. The story of entanglement is ultimately a story about the power of human cooperation in pursuit of truth. As we stand on the brink of the quantum age, with quantum computers beginning to demonstrate practical advantages and quantum communication networks starting to span continents, we can see the outlines of a future that would have seemed like science fiction to earlier generations. The strange predictions of quantum mechanics, once dismissed as impossible or meaningless, are becoming the foundation for technologies that could transform every aspect of human civilization. Yet for all our technological progress, the deepest questions about quantum entanglement remain as mysterious as ever. Why does the universe operate according to quantum rather than classical principles? What determines which interpretation of quantum mechanics, if any, correctly describes the underlying reality? How do quantum systems transition to classical behavior? And what does this tell us about the nature of observation and measurement? These questions might never be fully answered, representing permanent limitations on human understanding rather than temporary gaps in scientific knowledge. But the pursuit of answers continues to drive scientific progress and technological innovation, ensuring that the story of quantum entanglement is far from over. In the end, quantum entanglement teaches us humility about the limits of human intuition, while simultaneously demonstrating the power of human reason to transcend those limitations. Our everyday experience provides no preparation for understanding instantaneous correlations between distant particles, wave function collapse, or the measurement problem. Yet through careful mathematical analysis and ingenious experiments, we have not only discovered these phenomena, but have begun to harness them for practical applications. Picture two photons born together in a laboratory on Earth, then separated by the vast emptiness of space. One travels to a detector on Mars, while its partner heads toward the moons of Jupiter. Despite the millions of kilometers between them, despite the fact that no signal traveling at the speed of light could connect them, these photons remain linked by an invisible thread of quantum correlation. When astronomers measure one photon and find it polarized vertically, they know instantly that its distant partner will be found polarized horizontally, not because any information has traveled between them, but because they remain part of a single, indivisible quantum system. This image captures both the mystery and the wonder of quantum entanglement. In a universe that often seems cold and indifferent to human concerns, entanglement reveals a hidden unity that connects the most distant corners of space and time. We live not in a collection of isolated objects, but in a cosmos where quantum information weaves everything together in patterns of correlation and connection, that transcend our classical understanding of separateness. The strange idea that troubled Einstein has become the foundation for a new understanding of reality itself. The spooky action at a distance that seemed to threaten the rational order of physics has revealed deeper principles of connection and correlation that might ultimately explain the emergence of space, time, matter, and consciousness from more fundamental quantum relationships. As we continue to explore the implications of quantum entanglement and develop its technological applications, we participate in one of humanity's greatest adventures, the ongoing quest to understand our place in the cosmic order. The journey that began with philosophical puzzles about the completeness of quantum mechanics has evolved into a practical program for building technologies that could define the future of human civilization. The final chapter of this story has yet to be written, and perhaps it never will be. The universe, it seems, still has secrets to reveal about the deepest connections that bind all things together.